All right, so this is, and just some details with this. This is a practical resonance. Okay, resonance often used in microstrip circuits. Okay, so that's the reason for going through this, and it's very useful for microstrip lines. Okay, this is going to behave like a parallel resonant circuit. Okay, at multiples of lambda over 2. Okay, so just remember that every time you shift on your wavelength or the line, anywhere you shift on the line, these things are going to change. So when we're talking about this stuff, we are talking about a specific wavelength and a specific length of transmission line that holds the resonance on. Okay, so we're looking at open circuit, lossy, meaning but minimal loss, so not very lossy, of length L. Okay, so our input impedance for this type of a setup again is still Z0 hyperbolic tangent alpha plus J beta times L. So we're always starting with the same input impedance equation for all of these. And really, we're just applying what we get out of this right to this equation. Some mathematical manipulation of the equations so that they fit what we need to. We're trying to get it into a form that we can pull out R, L, and C values so we can actually calculate those values properly, and so we can get a Q factor so we know how well we're building this circuit, or how well it's going to run in our circuit, really. So we have that, and then we're going to say that this is, and I will sit down when I get to the bottom of this window because that's a little harder. So we're going to say this equals our Z0, not equals, plus 1 plus J. This is tangent beta L. This is hyperbolic tangent alpha L. And this is hyperbolic tangent of alpha L in the denominator plus J tangent beta L. And as before, most of this part is actually not going to change too much aside from the open circuit versus the short circuit. And that'll affect stuff down the line. So you'll see. We'll get there. All right. So as before, we have L equals lambda over 2. All right. And then this is at omega equals omega naught. So our resonant frequency is our length of lambda over 2. But we do want to replace this omega equaling omega naught with omega equals omega naught plus some delta omega. So we want to see what's happening off of the resonant frequency. Now for this, we still have beta L equal pi plus, and let's just make sure I do this right, pi times delta omega over omega naught. Okay, so we are still in the half wavelength, not the quarter wavelength. And then therefore, so, oh, I'm sorry, not beta, tangent beta L. Okay, is equal to, right below it. It's too hard to squeeze in there. Is equal to, well, just placing that in there, tangent times pi plus pi times delta omega over omega naught. And then we can state that fairly easily. This is approximately equal to, skipping a few steps in between, setting this all up and going through all of this. This is just delta omega pi over omega naught. Okay, so I just skipped the extra steps that were in there. And our tangent, hyperbolic tangent, is also of alpha L, is approximately equal to alpha L. Okay, and then therefore now our input impedance is equal to this. I'm going to write the denominator first, alpha L plus J, and this is J pi delta omega over omega naught, and this is my characteristic impedance in the numerator. And then when comparing this to a parallel circuit, right, so we're looking at the equations for our input impedance for a parallel circuit, we can pull out RL and C values. So R is therefore equal to Z naught over alpha L. Our C value is pi over 2 omega naught, Z naught. And then our inductance, therefore, is 1 over omega naught squared times C. And our unloaded Q factor, that's the Q naught, is just omega naught RC. And that is equal to, pi. Let's fix that so it looks prettier. C, which equals to pi over 2 alpha L, and that is beta over 2 alpha, and this is beta over 2 alpha since L equals pi over beta at resonance. Okay, so that is the construct for, or the way we design or manipulate the equations to get these. We should be able to use this to evaluate a microstrip line. So some of this is just a little bit of derivation to show you what the answers mean or where they're coming from and why you're getting these perturbations in here and how we simplify some of this stuff and the assumptions we make. Always keep in mind the assumptions that we're making when we're doing this type of thing is that we're considering low loss. So if you try to apply these equations to a very lossy line, you're going to get a lot of error. So keep in mind your assumptions when you're designing. And really just when you're evaluating. You just have to understand what you're doing or what you're evaluating and why. So we can apply the correct equations or if you need to do simulation in order to verify your numbers, which you would always do anyway. So the last thing we have to do for this video is actually go through an example problem. So let me clean off this board, see if I can squeeze a whole example problem into one board so I don't have to erase it again. I'm not making any promises, but I will try my best. Okay. From your textbook, this is example 6.2. This is a microstrip line resonator constructed of half wavelength, 50 ohm open circuit microstrip line. So this is set up like this. Let me see, where's my glasses? Let's look at this. Let's write what I can down. This is example 6.2 from your textbook. This is set up like this. So you have some open circuited microstrip line coming in. I'm drawing it off of here because I don't want to consider the off fringing effects. So essentially I'm just drawing a trace in the middle of a board. But that's essentially what this is. So we are looking at this, some of the details for this. This is a microstrip line resonator. So M microstrip resonator. So that, and then this is also half wavelength of 50 ohms. This is right from the book. And this is an open circuit, CUIT, if I can spell today. Okay, open circuit microstrip line. Okay, so microstrip resonator, open circuit, good to go. We also have the substrate is Teflon. Okay, and we have this from before. Epsilon R for Teflon is 2.08, and our tangent gamma is 0.0004. So if I remember that correctly, yes I do. And we also have a thickness of 0.159 centimeters. Okay? And it is a copper conductor. Okay? So we got a few things to work out. No problem there. We want to find the length, GTH, sorry, for resonance at 5 gigahertz. Okay, so we're trying to find a resonance at 5 gigahertz. We're trying to calculate how long it would need to be in order to resonate at 5 gigahertz. All right, and we also want to find the unloaded Q. Okay, all right, so your textbook, and I've done this in class. I did this example problem in class. I don't know if you remember it or not, but from chapter 3, we did find the width of a 50 ohm microstrip line in this substrate, in a Teflon substrate. So we're going to use that. So we're going to say the width equals 0.508 centimeters, and this is from chapter 3. So you can look this up or recalculate it. Both are fine. Actually, you probably should recalculate it just so we can keep in mind how we got that number. But it's in your textbook. So we need, that's the width, and had an effective permittivity, epsilon E, of 1.80. And you don't really need the 0, just 1.8 is fine. It's just, your textbook puts the 0 for some reason. So that is your effective permittivity. We need to calculate the resonant length, right? So resonant length, L, is equal to lambda over 2, okay, which is our phase velocity over 2 times the frequency, which is equal to C over 2 times F times the square root of the effective permittivity. Now we're going to plug all this in. L equals, and I'm going to write this, I'm going to do the denominator first so I can write this prettier. This is 5 times 10 to the 9, if you're still confused about my chicken scratch notation, times square root of 1.8, and then the numerator is C, so that's 3 times 10 to the 8 meters per second. And this is, I'm going to write it in centimeters because that's what your book does, but if you did this in a calculator, you'd have to convert. So 2.24 centimeters. So that is the length. My propagation constant for this is beta equals, this is 2 pi f, so that is my frequency times the phase velocity, right? So we don't do everything in omega. Most of the time you're given an actual frequency value, so 5 gigahertz, so we just always replace that. And then changing this around, we don't want to leave it in phase velocity, so that's just 2 pi f square root of E, epsilon E over C, right? And then this is then equal to 2 times pi times my frequency, which is 5 times 10 to the 9. And then this is also times 1.8, square root of 1.8 over 3 times 10 to the 8. And this is actually 151 radians per meter. Then we need to do exactly what we did with the last one. We have to find the attenuation due to the conductor loss and then the dielectric loss in order to go through properly and get all of our numbers for our unloaded Q. So you always need to go through the attenuation due to the conductor and the dielectric loss in order to get an unloaded Q. So we're going to do the conductor loss for this, and this is going to be RS over Z naught times W, and this RS is, where did we do that? We got that from 1.84 times 10 to the minus 8, and we got that from, where is it? Oh, that was already pre-done. Okay, so that is 1.84 times 10 to the minus 2 over 50, our 50 ohms. And then it is our width, which is 0.00508, right? We did it in centimeters. We need to convert it to meters. All right, and then this is equal to 0.0724. And this is in Neppers per meter. We have alpha D, which is our attenuation due to the dielectric constant. This one's a little lengthier because all the equation's a little messier. So K naught, I'm going to write this a little bigger, and then I'll just write Q naught down here. Okay, so alpha D, just so I can write it a little bigger. It's not so small. And this is K naught epsilon R times epsilon E minus 1 times this tangent gamma over and of course the pen's deciding it does not like me today. There it goes. Much better. Okay, times 2 square root epsilon E, and then epsilon R minus 1. There we go. There we go. That looks a little better. And then this is plugging in all these numbers. You can look these numbers up. We have this. K naught is 104.7, and then epsilon R is 2.08. Epsilon E minus 1 is 0.8, and then tan gamma. And we have all these numbers, so I don't want to fill in all of this with some numbers, but the answer is 0.024, and this is also in Neppers per meter, right? And they should be in Neppers per meter because you would add these together for any Q value. Therefore, our unloaded Q value, Q naught, is equal to beta over 2 alpha, and this is just 151 over 2 times, and there are 0.0724 plus 0.024, and then this just ends up being 783. So these are the numbers we're looking for when we're trying to find the length, well, obviously the length of the resonance, so that's one thing we were looking for. And then how to actually calculate our Q value, which we would need our propagation constant and our attenuation coefficients. So not too bad. So by next week, our goal is to do record or do some power dividers and couplers. That will be the first order of business, some basic properties of dividers and couplers, and some S parameters and how we actually simulate those. I'm going to try to make a good simulation over the week. I'm not sure if I'll be able to get to it. Most of this stuff is matrix manipulation, so it's a little math heavy. But as soon as you understand it, and we can verify our findings of the equations with the vector network analyzers, we'll be able to analyze any of our microwave engineering boards that we're making. So thank you very much. I hope you enjoyed the video.